Hello, everyone, and welcome to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. Today, we are going to talk about some really fascinating types of matrices. You'll find them in linear algebra, symmetric, involutory, unitary, and Hermitian matrices. And you know what's amazing about them? They aren't just these abstract math things. They pop up everywhere, from how we build bridges to the way quantum mechanics works. It's crazy.
Yeah, you're absolutely right. They really are like specialized tools. Each one is kind of perfectly designed for a very specific job. Like take symmetric matrices, for example. You can tell them apart really easily. They mirror themselves across the diagonal. So if you flipped one over, it would look exactly the same.
Like they have this perfect sense of balance.
Yeah, exactly. And this balance, the symmetry, it actually leads to some cool stuff. For one, it means that all their eigenvalues are real numbers. This is super important in things like engineering. Like imagine you're trying to figure out how a bridge vibrates. Those eigenvalues, because they're real, tell you exactly what the stable frequencies of that bridge are. And that's critical information if you want to make sure the whole thing doesn't fall down.
So the math is like a mirror of what's really happening with the bridge.
That's so cool.
Yeah. And speaking of connections, I remember learning that symmetric matrices are always square. Does that tie into any of their other special powers?
Absolutely. Being square is basically a requirement for another really important thing about symmetric matrices. They're diagonalizable. What that means is we can break them down into a much simpler form by using eigenvectors. And that makes things way easier to calculate. Like imagine you have this massive data set. Diagonalization lets you break it into smaller pieces. And then you can start to see hidden patterns and connections that were totally hidden before.
That's awesome.
Yeah.
It's like taking something super complicated and making it make sense. So, okay, let's talk about something that sounds kind of mysterious. Involutory matrices. What makes them so special?
Well, involutory matrices have this really cool trick. When you multiply one by itself, you get the identity matrix. So it's kind of like it undoes itself. Think of it like a light switch. Flip it once the light's on, flip it again, it's off. Back where you started.
That's such a good analogy. So they have to be square too, right?
Yes, they do. But unlike symmetric matrices, their eigenvalues can only be +1 or -1. It's like they have this binary nature, and that's what makes them so valuable in fields like cryptography, where you need to keep information secret and encode and decode stuff securely.
It's almost like a secret code. You can lock and unlock information with this special key, which is the involutory matrix. All right, so now let's dive into the world of complex numbers with unitary matrices. I know they're all about keeping lengths and angles the same in these complex vector spaces, but what does that really mean in a way that makes sense?
Okay, think about digital images, like the ones on your phone. Those are made up of pixels, and we can represent those pixels as vectors. Now, when you edit an image, like rotate it, resize it, add a filter, what you're actually doing is changing those vectors. And unitary matrices make sure that while all that's happening, the connections between those vectors stay the same. So the image might look different, but the important stuff, the basic information of the image is still there.
So they're like the protectors of the digital world, making sure your cat meme stays safe no matter how many filters you use.
Exactly. And they do all that by keeping this careful balance between their conjugate transpose and the identity matrix. It's kind of like a balancing act. And it makes sure that the distances and angles between those vectors stay consistent even when we're messing with them in all these complex ways. And because they're invertible, we can always undo those changes and get back to the original image. That's super important for things like compressing images, where you want to make the file smaller but not lose any of the good stuff.
It's amazing how these kind of abstract math ideas have such a real impact on things we use every day. Okay, so last but not least for this part of our conversation, Hermitian matrices. They sound pretty important. Being named after Charles Hermite, a famous French mathematician, what makes them stand out?
Well, Hermitian matrices are really interesting because they connect this abstract world of math with the real physical world, especially in quantum mechanics. And the thing that defines them is that they're equal to their conjugate transpose.
That sounds pretty specific.
It is.
Yeah.
And it leads to some really big results.
Yeah.
One of the most important is that all their eigenvalues are real numbers. And this is huge in quantum mechanics because Hermitian matrices represent things we can actually measure, like how much energy a particle has or its momentum. The fact that those eigenvalues are real means that when we measure things, the results we get are going to be real numbers too, which makes sense, in the real world.
So it's like they translate this abstract math language into something we can see and measure.
Exactly. It's like they're the bridge between this really complex math and the world we live in. And they're especially important in this field called quantum mechanics.
It's like they're a decoder ring helping us make sense of all this quantum craziness.
Yeah.
So what else makes Hermitian matrices special? What other cool things can they do?
Well, they always have to be square, like we've been seeing with all these special matrices. And just like those symmetric matrices we talked about, Hermitian matrices can be diagonalized. But there's a bit of a twist to it. They're diagonalized by a unitary matrix.
Okay, wait. Let's back up for a second. We were talking about unitary matrices before. They're the ones that keep the lengths and angles the same in those complex vector spaces, right?
That's right. And this connection between Hermitian matrices and unitary matrices is really important because it shows this fundamental rule in quantum mechanics, this idea of keeping information safe. So when we diagonalize a Hermitian matrix using this unitary transformation, it's kind of like we're changing our viewpoint. We're looking at the system from a different angle, but we're not losing any of the important information.
So like if you're turning a Rubik's Cube, the colors might move around, but they're all still there.
Exactly. The essential information is still there. It's represented by those eigenvalues. And this is crucial for understanding how these quantum systems change over time. We can describe these changes using Hermitian operators, like something called the Hamiltonian, which is all about the total energy of the system.
Wow, that's pretty mind-blowing. It's like you're looking behind the scenes of reality, seeing how the universe works at the most basic level.
And what's even more amazing is that these mathematical ideas, which might seem really abstract, actually have real-world applications in all these new technologies, like quantum computing.
Quantum computing. That sounds like something straight out of a sci-fi movie.
I know, right? But it's actually becoming real and fast. In quantum computers, information is stored and processed using these things called quantum bits or qubits. And they can exist in this weird state called superposition. And you know what? Unitary matrices are what we use to describe the operations, the quantum gates that we can do on these qubits.
So instead of just switching bits between 0 and 1, we're actually like rotating qubits in this multidimensional space using unitary matrices.
You got it. That's a great way to think about it. And because unitary matrices are reversible, it means that quantum computations can happen without losing any information, which is super important if you want to build quantum computers that actually work.
It's incredible how these matrices are at the forefront of this whole new technological revolution. Okay, so we've gone through these 4 awesome types of matrices: symmetric, involutory, unitary, and Hermitian. And they all have these unique characteristics that make them so important in so many different fields, from engineering to cryptography to quantum mechanics. It's amazing.
And we've really only just scratched the surface. The world of matrices is huge, and there's so much potential waiting to be discovered. As we dig deeper into how they work, we'll be able to understand and change the world around us in new and exciting ways.
It's like we've been given the keys to this secret language, a language that tells us about how the universe is structured.
And just like with any language, the more we learn, the more we'll be able to understand and appreciate the complexity of the world around us.
It's a journey of discovery that I can't wait to keep going on.
And remember, learning never stops. There's always something new to find out, new connections to make, and new ways of seeing things. So keep exploring, keep asking questions, and stay curious.
So where do we go from here? What else can we explore?
Well, we could really dive into the specifics of how these matrices are used in different areas. Like we talked about Hermitian matrices in quantum mechanics. We could look at specific examples like the Hamiltonian operator. That's all about the total energy of a quantum system.
Oh yeah, the Hamiltonian. I remember that from my physics classes. It's kind of crazy to think that something like a matrix can describe such a fundamental idea in physics.
It really is. And the Hamiltonian is so useful because it helps us predict how a quantum system will change over time. When we understand its properties and how they connect to Hermitian matrices, we can learn about things like energy quantization and quantum tunneling. It's fascinating stuff.
That's wild.
Yeah.
It's like we're using matrices to crack the code of the quantum world.
And the cool thing is these applications go way beyond quantum mechanics, like symmetric matrices. They're super important in fields like machine learning and data analysis. They show up in techniques like principal component analysis, which is used to simplify data and keep the most important parts.
So instead of trying to figure out this giant, messy data set, we can use symmetric matrices to find the key features and patterns.
Exactly. It's like finding a needle in a haystack. And this technique is everywhere, from facial recognition software to financial modeling.
It's amazing how these abstract mathematical ideas end up having such a real impact on our lives.
It really shows how powerful and beautiful linear algebra is. It's often overlooked, but it's the foundation for so much of science and technology and even art.
Art? Wait, you mean matrices are hiding in our paintings and sculptures?
Haha, not literally. But the principles of linear algebra, like transformations and geometric relationships, are essential for understanding things like perspective proportion and symmetry in art. Think about the Renaissance artists. They used mathematical principles to create these incredibly realistic paintings and sculptures.
Wow, I never thought of it like that. It's like math is woven into our culture and how we see the world.
It really is. And the more we explore matrices, the more we realize how deeply connected they are to everything we do and experience.
This has been such an awesome journey exploring the world of matrices. We've learned about their special properties, how they're used, and how they connect to the world around us. It's been mind-blowing.
I hope this has made you curious to keep learning about linear algebra. There's so much more to discover.
Absolutely. It feels like we've only just scratched the surface. There's a whole universe of knowledge out there.
And remember, learning is a lifelong adventure. There are always new connections to make, new insights to gain, and new possibilities to unlock. So keep exploring, keep asking questions, and never lose your curiosity.
That's great advice. Well, on that note, I think it's time to wrap up this episode. Thanks so much for joining us on this mathematical adventure.
It's been my pleasure.
And to all our listeners, stay sharp and stay curious. We'll see you next time for another exciting journey into the world of knowledge.